single bond, like in ethane, it can rotate. Or like cyclohexane, we talk about conformations as rotating around bonds. And that's great, and that leads to all the stuff we talked about that leads to. Double bonds and triple bonds can't do that, because if they rotate, those p orbitals are no longer going to be lined up with one another, and as soon as they get misaligned, there's no longer a bond there. So a sigma bond, where the lobes are just kind of smashed into each other, can rotate and still be bonded. But the pi bond, that's kind of like almost bracketed on either side, if it rotates, they're no longer aligned, they can no longer bond. So that means that double bonds and triple bonds lock a conformation into place and will no longer rotate. And that means that structures or molecules that differ by their arrangement around a double bond like these two molecules I'm drawing here, are not the same. If that were a single bond, those two would be the same, because one could just kind of twist and we'd make one out of the other. But when they're locked in place, we can't make one out of the other. So if I make a model of this, so here's that first one. There's no way I can make the second one out of the first one without pulling one of these off and switching it somewhere. Because I'm locked in place now, I can no longer rotate that. And that means that these two things have a relationship to one another that's a little bit different from what we've seen so far. They're not isomers in the sense that we've talked about isomers so far, because they do still have the same connectivity. It's 4 carbons connected in a row. The hydrogens are still connected to the carbons they would be connected to. They're the same in that way. They're not conformations, because conformations are actually the same molecule that just differ from rotation around a bond. And as we just talked about, these don't rotate. So there's something different. And that different is called stereoisomers. They are stereoisomers of each other. And what stereoisomers are, we're going to do a whole chapter about that next, but for now, they only differ by spatial arrangement. So everything else is the same. Molecular formula is the same. They're connected in the same way. But in space, they're different. So something's in a different spot than something else. That's what we mean by spatial arrangement. That there's something different about them, but it's not that they're connected in different ways. Anybody have a guess as to what types of words we're going to use to differentiate those two from each other? Right, cis and trans. So if you had to guess, which one would you call cis? Excuse me. Yeah. The what? The second one? Yeah, the second one. Why? You're right, but what brought you to that? Because you got it wrong on the test. Yeah. Yeah. So when two things are the same like that, what we do, I like the motions of it. Yeah. What we can do is kind of imagine a line that goes parallel with the double bond. And if the two things that are the same, like the two hydrogens, are on opposite sides of that line, we would call that trans. And if they're on the same side of that line, we would call that cis. Yeah, that's the tricky part about this, is in order to name it cis and trans, you have to have the same type of thing on both sides. So in this case, we could either look at the hydrogen or the methyl groups, because they're both the same, but with bigger molecules, that might not be the case. And if the molecules actually have all different stuff on there, then we have to do something else. We'll get into that next. So let's talk about how to name alkenes and alkynes basically, or in general first, and then we'll get into the specifics of this cis and trans and how we're going to add that. So remember, the point of names is to be specific and unique, so that when you say a chemical name, it only applies to one kind of thing, to one specific molecule and not other things. If we have a molecule like this, given what we just talked about, that we drop the end, or we drop the A and we put in an E and we make an ane and ene, how do you think this molecule should be named? Based on how many carbons it has. Butene. Everybody good with that? What about this one? Right. So this would also be a butene, but that tells us that our name isn't quite good enough. So how do you think we... Yeah, right. So we call this one 1-butene, and we call this one 2-butene. Because the double bond starts at carbon 1 in this first molecule, and number 2 on this one. What were you going to say? All right, so then what about this one? That's right. 2-butene because it starts at carbon number 2. So what would you call this next one? But we know that these are different because that double bond can't rotate. So what are we going to do to differentiate them? Right. So this one should be called trans 2-butene, and this one should be called cis 2-butene. Yeah. Same thing as before. So we imagine a line that goes parallel with the double bond. And if two things that are the same are on either side of that line, it's trans. If the two things that are the same are on the same side of that line, it's cis. So we could either look at the methyl groups here or the hydrogens that are not shown that are coming off this way. So those are the same molecules that we drew up here in line structure. So there's our trans and there's our cis. All right. So the only other thing you need to know about naming, well, a couple things, but the next thing you need to know about naming is that an alkene actually takes precedence over those other substituents we looked at in terms of the numbering. And that's because the alkene now is a reactive center. In 2 chapters, we're going to start to talk about reactions of alkenes and how we can use alkenes to build up molecules and do other stuff with them. So a molecule is kind of controlled by its reactivity, and that means that the alkene or alkyne is going to get preference in naming. And then I'll show you what that looks like. So let's take this molecule. What's the longest chain here? 6. So how would you name it? Hexane. But it's hexene because of the double bond, right? And here's where it's different. Normally, if this were not a double bond, we would start numbering on the right because that's closer to the substituents. Remember that? But the double bond gets the preference. So we start over here and go 1, 2, 3, 4, 5, 6. And that means that the appropriate name of this molecule should be what? We still name the substituents first.
We can't start with the word hexane, right?
That's right. So that will still go at the end. Well, that's another thing we have to decide. Is this a cis or trans double bond or neither? Neither in this case, because this carbon's going to have 2 hydrogens on it. So this one's going to be 4, 5, 5. Trimethyl 1 hexene. Right. If it's at 1, it is usually assumed, but it's always a good idea to put that one in, especially with larger molecules. Another way you can do that is also appropriate and fine is you keep everything else the same. But you move that 1 to where the ene is. So you're specifically talking about where that alkene is. So some people prefer to put, some people find it less confusing if you move that number right at the suffix, right before it tells you where that double bond is. Either way is fine. Right. Right.
Okay. So if it has any double bond, it's en.
That's right.
It's suffix.
Your coach is right.
Okay, and then why isn't it cis or trans for these?
In this particular case, there's no difference between the two sides. So if we do the same exercise where we imagine a line here, on this side we have the same thing on both sides of that line. So there's no way to compare it to the others and say it's either cis or trans.
So it's only about what's going on.
Right.
Not the rest of it.
Not the rest of it, because the rest of it is all rotatable. It can do whatever. All right, let's look at another example of where this can get weird. Not weird, I guess, but different than what we're used to. So here, this is a common mistake that I'll see if somebody's trying to name this. We need to number this ring. And you remember that the double bond gets precedence, right? It's preference. So where's the 1 going to go? Yeah, right here, right? Because that's a methyl group. We want that to have the lowest number. So then where should we put 2? That's right, and that's what tricks some people or trips some people up. If 1 is here, then that double bond has to go between 1 and 2. We can't suddenly go this way and have a double bond between 1 and 6. So we have to continue numbering along that double bond. So we'll go 1, 2, 3, 4, 5, 6. So even though those two methyl groups are right next to each other, this name ends up being 1, 6, dimethyl, whoops, not hex. one ene or one hexene or just hexene. Now we don't say cis or trans usually in small rings like this because you can't have a trans alkene in a ring. There just isn't enough room for it to loop back around if it were going off that way. So it has to be cis to come around and close the ring. So we assume that. That's not true for really big rings, but we will encounter a lot of those. All right, so now we know almost everything we need to know about naming alkenes. So we'll put the last little piece in place and we'll be good. And then we'll take a little break and come back and talk about other types of stereochemistry. All right, so the last bit here is what happens when it's not just cis or trans, and the rules that we talk about now are going to become important in the next chapter too. So let's say we have an example like this. The book, I don't think, does a great job of, we'll get to it. Let's say we have this alkene. Let's draw it as a line structure too, just so we can see both ways how it looks. So we can name this, I think, all but one little part. So let's try to get the main name. What is the longest chain here that includes the alkene? 5. And we want the alkene to get the lowest number, so where are we going to start our numbering? Over here, right? So 1, 2, 3, 4, 5. 4, 5. Yeah, agree? Okay, so then what should that name be? Pentene. Okay. And what number? What type of pentene? Yes, this is going to be a 2-pentene or pent-2-ene if you like that better. And what about the substituent? What kind of substituent is on there? Right, so it's 2-chloro. Everything else is the same as the naming we've already done. So this is going to be 2-chloro, 2-pentene. But now we've got a little bit of a problem, because if we try to make our line here and decide if it's cis or trans, there's too many different things. So you could say that the Cl is cis to the H, or the Cl is trans to the CH2CH3, or the CH3 is trans to the H, or you get what I'm saying. There's too many different possible relationships here. There's no two things that are the same that we can say those two things, those two hydrogens are trans to each other or are cis to each other. It's too complicated. So that means we can't use cis or trans. We have to come up with a new way of arranging these. And the rules that we're going to look at are called E and Z. So rather than cis and trans, we've got E and Z. And they will tell us something about this relationship. What we're going to do is rank the two groups on either side into priorities. We're going to say this one has higher priority, this one has lower priority. And then we're going to use that to determine which way we call it. Do you have a question?
Yeah. I guess I'm very confused.
Yeah.
Why is methyl?
Because that's all part of the chain. That's all part of the pentene. Right, so our main pentene chain here is this. All the connected carbons. Like here. So the only thing not included in that is the chlorine. It could be if there were other stuff there, but it's not in this case.
And then how do you
So it'd be here 1, 2, 3, 4.
Wait, but
Five.
you number it differently?
It means we have to start from where the alkene gets the lowest numbers. So we can't start from the right. We wouldn't in this case anyway. We still start at the end, but we want the alkene to be at 2, not at 3, which it would be if we started from the right. All right, so the basic idea of this is we're going to look at our two sides of the double bond, any double bond, and we're going to rank the two things connected to a carbon into a higher and lower priority, and I'll show you how to do that. And then we're going to look at the two higher priority groups on either side and decide whether those are cis or trans to each other. And that's how we're going to make this determination. So if it looks something like this, where we imagine that line in that double bond, and we see that the higher priority ones are on opposite sides of that line, we call that E. Comes from German, so not necessarily intuitive why that would be E, but E is like the trans type version of this.
We know what that's.
We're going to get to that next. Yeah, we're going to get to that. And so if the two higher priority ones are on the same side, then that becomes Z. So let's look at our example and figure out how we rank these. Okay. So the rules, if you have this edition of the book, the official rules, priority rules, are on page 115. Probably something you want to go over, but I'll go over them as well right now. So first, the first priority rule is pretty easy. Atomic number. So if something has a higher atomic number, it has a higher priority. So chlorine is going to get priority over carbon, for instance, because it has a higher atomic number. Carbon gets priority over hydrogen. So that's the first thing you look for. Okay, so let's see if just using that rule we can solve this one example that we've got. So let's look at the carbon on the right first. Carbon 3 here. So between the two groups, which one are you going to give higher priority? Right, this right here. Now remember, we're only looking at one atom, so we're only looking at the atom directly connected, and we compare the C to the H, and we say, oh, C has a higher atomic number than H, so this one gets our higher priority. So we'll put a star here, or something, some kind of mark.
Okay, you always look at only that first.
You just look at one carbon, the two things that are connected, and you give a priority to one or the other. So now let's look at the other carbon. It's got two things connected. Which one has priority? The chlorine, for the same reason. Okay, so now you look at those two higher priority groups, and are they on the same side of that line or opposite side of that line? Opposite, right? This one's up here, this one's down here. So that tells us that this is going to be E. So we put an E in parentheses at the beginning of that name. So it becomes E2-chloro-2-pentene, and that's the correct complete name. So now let's look at what happens when that stops working. Let's look at the next priority rule. Miss a little more room here. So the next example is going to look like this. And we're going to use a line structure so we can get used to that also. We'll use a chlorine again as well. All right, we won't mess with the name just now. We'll just look at the E and Z because that's what we're talking about. So we're going to look at the 2 carbons involved in this double bond and imagine a line running parallel through that double bond. So this first carbon here, which side gets priority? This or this? The chlorine gets the priority, right? For the reason we just talked about. On this side, we can't make that distinction because we've got carbon and carbon. So it's a tie. So what do you think we do? Yeah, you just move to the next thing and do the same thing. So you move to the next thing it's connected to, and you make the same comparison. So this carbon is connected to what? This one up here is connected to what? Well, yeah, but over on the other, going away from the double bond, hydrogen. So it's connected to 3 hydrogen, right? It's a carbon that's got 3 hydrogens on it. What's this carbon connected to? 2 hydrogens and another carbon. So 2 hydrogens in a carbon beats 3 hydrogens, kind of for the same reason, because carbon beats hydrogen. Yeah, so this one does too, but we don't count. So we don't count these, we don't count it as a whole group and say this whole group has priority over this whole group. We look atom to atom and we say, oh, carbon, carbon, that's a tie. So what's the next highest one? This one's highest connection is a carbon. This one's highest connection is just a hydrogen. So we go one more step. We only see hydrogen on one side. We see carbon on the other side. So we can make the priority that this side has the priority. So then what is that? Does that make it E or Z? This is now Z because those 2 higher priority groups are on the same side of the double bond. So the total name here would be Z. I guess we go 1, 2, 6. So that would be Z, 3 chloro, 4 methyl, 3 hexene. The rest of the naming's the same, and then we stick that Z at the front.
So, question, what if that last carbon wasn't connected? So it would be CH3 on one side, CH3 on the other.
Then it can't be E or Z because there's no difference in the 2. So it's just
Leave it.
just leave it. Yeah. Yeah, if there isn't a difference in the 2 sides of one, then it doesn't get an E or a Z or a cis or a trans or any of that. But
Second priority rule?
what? Yeah, so the second priority rule it's kind of the same as the first priority rule. Second priority rule says if the atomic number isn't different, if no difference, yeah, that's right. If there's no difference, look at the next connections, or the next connection. So what's the next highest one? What is it connected to? So let's look at some examples here and try it out. I'll give you a couple. Give this one a try. And then if you get that one, try this one. So try to find the whole name of these, work together. See if you can find the name of these two compounds.
So you know how you usually number 1, 2, 3, 4, 5, 6,
Yeah.
7, 8, 9, 10. You would number in a way where that would bother the lowest number.
Yes, but you still need the longest chain.
Oh.
So you would still start at the far right and number that way. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Once you've got your head already one. Just be that. So at first they're tied, C and C. Then when you step one away, you get C to H. Be careful of collapsing it down to the standard form. Make sure to keep the same geometry. Thing there. So it's important whether it's on one side or the other side. Well, flatten it out. It's not clear necessarily which side that's on. Like if you want to turn it into this type of form, that's fine. But I would, don't collapse the bonds to 90 degrees and bond angles as they are. That should be so we get 6 and so this one. Oh yes, you can just try and see. So you can also do it. Yeah. You look at each carbon as a double bond. This carbon is a double bond. And then you compare the two things that are connected to it.
So this is the
Yeah. Yeah, so you've got C and C, so that's a tie.
Yeah.
And This carbon's with hydrogen, whereas this one's with carbon.
Yeah.
So this one's that's what it's saying.
So then where would you put that?
Yeah. Well, you look at what's connected, so you've got carbon and carbon at the top. This one connects to hydrogen. This one connects to carbon. Right. So then you match the line. Same side. Right. Yeah. Well, it would be all the way down here. But you're looking to carbon. This one. Carbon middle. So you're trying to So that's it. So then you can say the when you look at the two higher ones and see if they're on the same side. Right. 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 Yeah. So the same thing. So you go right tie there. Go one more carbon. Still carbon. Well, yeah. Okay, so first you'll potentially look at the other side. Right. So what are the two of this carbon? That CH3 on the side to the side. What's connected to carbon? It's not sure which one is the one is the hydrogen. Well, the higher priority is this one. These two keep going, so those are higher.
Here's the line.
Yeah, what is actually there? It's not showing. Yep. Well, yeah. What's his priority? Yeah, say, see the one more. That one. Right. So this one has 3 hydrogens connected to it. This one has 2 hydrogens and a carbon. So the carbon no. This side is very aggressive. This side is very aggressive. That's All right, let's look at these. So for this one, again, you want to look at the double bond, right? And then each carbon of the double bond. So we take this carbon, just this one, and we look at the two things connected to it, and they're both carbons. So that's a tie. So then you say, well, what's connected to that carbon? Just 3 hydrogens. What's connected to this carbon? 2 carbons and a hydrogen. So this one wins. So this side wins. That gives us our priority. Now we look at the other carbon, right here. Carbon, carbon connected to it. Those are tied. So what's connected? Well, this one has 3 hydrogens connected. This one has 2 hydrogens and a carbon. So that carbon makes it win. So this side wins. You look at those 2 stars, they're on opposite sides of that line. So that makes this what? E. So the full name of this should be E 2, 3, 4 trimethyl 3 heptene, 7 carbons. Okay? Same exercise for the next one. Let's look at this bottom carbon first. So we've got a carbon on this side. There's nothing on the other side. What does that mean? Yeah, so that's not shown because it's a line structure, but there's a hydrogen over there. And so carbon beats hydrogen, so this side gets the priority. Then on the other one, we look at these two. We got a tie, carbon, carbon, and they each have 2 hydrogens. So then that's connected to a carbon, that's connected to a carbon, still tied. Then when we look at these, we see that this carbon has 3 hydrogens on it. This carbon has 2 hydrogens and another carbon. So that extra carbon coming off of this one makes kind of as the tiebreaker to give that priority. Those 2 higher priority groups now are on either sides of the line. So that is also E. So this one's going to be E 3-ethyl 2-hexene. Because you're going to start numbering down here. Go 1, 2, 3, 4, 5, 6 to give the double bond the priority. All right, I know this stuff is weird when you first look at it. It does take some practice and some kind of going over in your head and working on it, and eventually it'll kind of click and you'll think, oh yeah, that makes sense, I've got that. Some of you may be getting there already, some of you not, but that's fine, we will get there. Let's take a 10-minute break and then come back and talk about what happens with this with not double bonds. We'll go back to single bonds and talk about how we have to deal with some of these priorities.